Video is sponsored by a puddle of platypuses. Okay, rational functions. Anytime you have a rational function on the top and a rational function on the bottom, I mean a polynomial on the top and a polynomial on the bottom, it makes a rational function. We will exclude ourselves to parabolas and lines and constants. So you could have 6 over x squared plus 5 and have to graph it, because that's a constant over a parabola. You could have a parabola over a parabola, a line over a parabola, and that makes all of them will fall under group 1, where the degree was bigger on the top, group 2, where the degree was the same on the top and the bottom, or group 3, where the degree was bigger on the bottom. And we'll go through characteristics of each of these, and the first characteristics that we look for is non-permissible values. Non-permissible values will turn into one of two things. They will either be wholes if they cancel out and go away, or they will be vertical asymptotes if they stick around. So in this first function here, the bottom's already factored. The non-permissible values are 3 and -1, because that would make us divide by 0. They do not cancel out, so they become vertical asymptotes. And our job will be to graph this. Do you see that this is group 3? The degree on the bottom is a parabola, the degree on the top is a line. And group 3's characteristic is when the degree is bigger on the bottom, you had a horizontal asymptote at y equals 0. But that's not characteristic 1. Characteristic 1, we're just thinking about non-permissible values. So in this example, they don't cancel out. The second example in your notes, the non-permissible value of x minus 3 cancels out, leaving you just with the new equation simplified as x plus 1. But you still have that non-permissible value of 3. You would now graph y equals x plus 1 and add a hole. So this graph has a hole, and to label the hole happens at the non-permissible value, so the x value that's non-permissible is 3. And to find the y coordinate of the hole, you'd say, well, if I graphed y equals x plus 1 normally without a hole, I would have had the point 3, 4. Plugging in 3, x plus 1 makes 4. That normally would have been the point, but since that's not allowed, that is now the coordinates of the hole. So we find the coordinates of the hole by plugging in the non-permissible value into the new equation. Sometimes you could have this situation. We have an x minus 3, but that would cancel out with only one of them. X minus 3 would still be a non-permissible value that's on the bottom. In this situation, both the non-permissible values stay as vertical asymptotes. So the hole only occurs if a non-permissible value cancels and goes away and is no longer a non-permissible value. In this situation, you still have the 3 as a non-permissible value after you've simplified. The graph doesn't have a hole in it. So to summarize, you will have a hole if the non-permissible value simplifies and goes away. You will have a vertical asymptote if the non-permissible value doesn't simplify and go away. Okay, now, on your bookmark that I gave you, you have these steps, which is kind of nice. You don't have to rewrite this right now. We can go a little bit faster. This question says to just do vertical asymptotes. What we are going to do is we're going to look at all the characteristics every time with every example. And these steps for graphing finishes the unit. But the unit's going to have more characteristics. We'll dive deeper into those characteristics with each example, but I'm going to show you the steps for graphing every single one all the time. And the reason is all the examples from 2.3 and all the examples from 2.4, they all add something just, a little bit different, a little bit different. The steps for graphing stay the same, but there's a lot of little different things that end up happening, and no two graphs really look the same. So it's kind of weird. So we need to do lots of examples just to get comfortable with the steps. But the steps themselves will stay the same. You're always going to start by factoring completely. So our question here in A, I can factor the top. X minus 5, X plus 5 over X plus 5. List your non-permissible values. Well, my non-permissible value, I'm dividing by X plus 5, so X absolutely cannot equal negative 5. And your non-permissible values will always end up being either a whole or a vertical asymptote. Look at our equation. Do things cancel out?
Yeah.
Yes. The X plus 5 would cancel out. And so this one is going to have a whole. And I wrote it in green here. I couldn't write it on green in yours. Maybe you want to highlight this note in a different color on your bookmark. But after they cancel out, and I'm going to write my new equation in green here, if there is a whole, you graph the simplified equation and add the whole. So I have a whole, because it's simplified, and I can write the coordinates of that whole. They're going to be at the x coordinate that was not permissible, negative 5. But if I have the simplified equation, normally that would have had a point if I plug in negative 5 at negative 5 comma negative 10. That's going to be where the whole is in the graph. And in example A, this note comes into effect. So you now graph the simplified equation. Do you know how to graph this? It's a straight line. In fact, we will not need steps 3, 4, and 5 for this one. Because once we got to the green equation, it's a graph you already know how to graph. So we graph that equation. X minus 5, 1, 2, 3, 4, 5. I know it would have a y-intercept of minus 5. It has a slope of 1, so it would have an x-intercept at positive 5. And over here, at minus 5, minus 10, I draw an open circle to label my whole. And this graph is done. So we had 5 steps for rational graphs. This first example only needed step 1 and 2 because the new equation in green was a line that used to know. I could give you a graph that started off as a parabola with an added hole in it. And you'd be like, I already know how to graph parabolas. I could just add the hole. I could put a question on your test with a log graph and add a hole to it. Right? I could get you to, here's one on your test tomorrow, right? I could get you to graph this on your test tomorrow. Right? You see that that's a log 3 graph? Move 1 to the left.
Yeah.
Okay? Okay. I could take this and times it by x plus 2 and divide it by x plus 2. Do you see that those x plus 2's would just cancel out? Giving you the same graph that you had to begin with. Except you'd have to add a hole when x was 2. So it'd be a log graph with a hole in it. You can, right? You like adding holes to graph? Any graph we've done already, you can add as many holes to it as you want. As long as you put something on top that cancels out with something on the bottom. Okay, so that's graph number 1. Graph number 1 in our bookmark only took us to step 2 because once we simplified it, the new green equation was x minus 5, which you already knew how to graph. You just had to add the hole. Yes.
If we have a hole in the graph, are we allowed to just draw one through it, or does it have to?
It has to have a circle there.
Okay.
That's empty because technically, like in calculus, this becomes really important because this is a point of discontinuity. The graph is no longer continuous because you'd have to, in reality, draw it, lift your pencil up, go on the other side, and put your pencil back down and keep going. And there's a gap in this graph. Okay, I am going to erase part 1 here. And we'll do B. I factor completely. In the top, I can take out a 2, leaving me with 2x plus 1. On the bottom, I have an x minus 2. I write out my non-permissible value. I factored completely. My non-permissible value, x can't equal 2. Does it cancel out? No. So this one, the non-permissible value is a vertical asymptote. That's step 2, our non-permissible values. Afterwards, we have to determine if there's a horizontal asymptote or an oblique asymptote. Question 2, which group is it? Group 1, group 2, or group 3? Same degree on the top, same degree on the bottom. This is group 2. Group 2 has horizontal asymptote at y equals 4 divided by 1, 4. So that's step 3. Step 4 says intercepts and nice points. So what we're going to do now is we're going to start graphing. And when we go to start graphing, we know our asymptotes. So we're going to start by labeling our asymptotes. We know there's an asymptote at x equals 2. And label that. And we know there's an asymptote at y equals 4. And we can label that. Step 4 is drawing some points on your graph. And we're always going to label our x-intercepts and y-intercepts. The y-intercept is the easiest one to start with. So I'll do that one first. How do you find a y-intercept? You plug in 0 for x. I'd probably go to my original equation. Do you see in your original equation, if you plug in 0 for x, the top is plus 2, the bottom is minus 2. So if I plug in 0 for x, plus 2 divided by minus 2 is minus 1. And I go to my graph now and go to 0, minus 1, and label that point. Next, x-intercepts. X-intercepts are when y is equal to 0. Now I'm going to show the math here, but there's going to be a shortcut. You wouldn't have to write this down. I like to go to my factored form, so I'm going to write out my equation with my factored form. And I need to solve for x when y is 0. Now there's something really nice that happens with fractions equal to 0. If you have a fraction equal to 0, does it make sense that the numerator, the top, has to be 0? It doesn't matter what the bottom is. 0 divided by 17, 0. 0 divided by 382, 0. It just matters what the top is. Technically, you could multiply both sides by x minus 2 to cancel that out. But really, I'm just going to highlight the top here and just say, can I see when that's going to be equal to 0? And if it's factored, check your factor out. What would make 2x plus 1 0? What makes that equal to 0? Negative 1/2. So you can just directly, I think you could just look at it and write down the x-intercept. Then I'm going to go to my graph. And label that point. Now, once you have labeled your x-intercept and y-intercept, sometimes you're ready to go to step 5, but sometimes we need some other nice points. And I'm going to talk about what this means, 1 point in each section. Okay? Technically, these 2 points, you have enough to do step 5 for this section. draw the graph towards the asymptote. So I know my graph goes through these 2 points. Well then, I can't go through the x-axis again, because once you found your x-intercepts, you have found them all. There's no more x-intercepts to find. So it has to go towards the asymptotes. That section is done. And when I say 1 point in each section, you're going to find out that your asymptote, your vertical asymptote, splits your graph up in this situation 2 sections. Left of the asymptote, right of the asymptote. So what I mean by nice points is you need a point in each section. I have no points right now in section 2. My x-intercepts and y-intercepts both happen to be in section 1.
Students, at this time, can we get all the grade 12 graduating students to please come to the theater? That's all grads or potential grads. Please come to the theater.
I'll post this all
Thank you.
online. You'll have to watch it later. Okay. So in section 2, we need a point. I'm going to pick any x value in section 2. Generally, I like to go 1 to the right of my asymptote. Sometimes I go 2 to the right. If I pick x equals 3, and I plug that back into my equation, so do you see right here, my original equation had an x here and an x there? I just plugged in 3. And when x is 3, I'm going to find out the point. Well, if I do the mental math here, 6 plus 1 is 7 times 2 is 14. I get the point 3, 14. If I had plugged in 4, this would be 8, 9 times 2, 18 divided by 2. I get 4, 9. I can choose just one of those. Like the reason I did 2 is because like 3, 14 is like, oh my goodness, it's way up here. This asymptote would just keep going. 4, 9, had I done that one, would have been a little bit more reasonable. It's kind of there. Still not the greatest. But once I have just 1 point, and I only need 1 point in this section, it's enough for me to draw my graph towards the asymptotes. And now this graph is done. Yes.
Let's say you're just like really struggling and you can't get the point on the other side. If you just draw it and don't label any points, you're still gonna mark.
Well, the problem is, how do you know that it's in the top half? It could have been in this section.
You gotta gamble.
You're gonna take a chance, but they will check that you've labeled 1 point in that section. I'll go to the back and then I'll go to Benjamin.
So you need 2 points in one section and 1 in the other, or do you just?
You need 1 point per section, but you need to find all of your x-intercepts and all of your y-intercepts.
Okay.
So by finding my x and y-intercept, I got 2 points in that section,
So what's
but
the,
one of them would have been enough to draw it all, but I need to label all of my x-intercepts and all of my y-intercepts.
Back to that gamble you was talking about, wouldn't you know if it was in the bottom right, because there'd be an x-intercept there?
Yeah, so in this one, it's a good gamble not to say the bottom, because if it was in the bottom, you'd get another x-intercept, which you know can't happen, so you knew it probably needs to be in the top. Okay? But you're just gonna find out that sometimes weird things happen, which we'll see in our graphs. And we'll go through some weird situations each time that we see them. But you can circle
I don't think.
question numbers, just question number 5 for this one.